Thank you for coming. Obviously, yes, I can see this has struck a chord. We are all programmers here, right? Is anybody here who's not a programmer? Okay, good. So let's be honest with each other here in the privacy of this room. We have a terrible reputation. Software, as you know, is a byword for unreliability and busted budgets. It's a joke that if something goes wrong, you switch it off and switch it on again. I have a head torch, and that head torch works off software. I know it works off software because it has a bug in it. And if we can't even switch a light on and off reliably, then we have a problem because the world works off software. Everything in the world works because of the software that's in it. Truth be told, seen from the outside, from our managers, from the users of our products, I'm sorry to say it, guys, but we're not very good at our jobs. And yet, the aeroplane that I came in on is flown almost entirely by software. I see the inside of a lot of hospitals which are full of machines which work by software that keep people alive. Our crowning glory, the internet, is so reliable that we can run the world's entire emergency services on it. And it was designed to be resilient in the face of attack. And with all of the political stuff that's going on at the time, you can see actually it's standing up to that reasonably well. When it comes to it, when it comes down to it, we can write software that we can entrust our lives to. And so I have a question. The people who build those systems, what do they do that the rest of us don't? That's what today is about. Is that interesting? Are you in the right room? Good. Okay, my name is Jules. I am a consultant, and that means I see the inside of an awful lot of companies. And everywhere I go, I get here the same thing. We're sorry. We didn't intend it to be this way. We thought this time it would be different. So I have a question for you, again, just to make sure that you're in the right room. If you asked me in to solve your technical debt problems or your reliability problems, would you feel the need to apologize for what you're about to show me? You wouldn't. It's funny, isn't it? I knew not one hand was going to go up, because actually this is the world we live in. But trust me, you have nothing to worry about, because I have seen something worse than anything you have got. This is the worst project I ever worked on, and it was the thing which pretty much defined my career subsequently. This was 2.5 million lines of code. It had been originally created in Fortran. It had then been translated into Delphi, and then translated into Delphi.net, and then into C#, it had bits of assets from all sorts. At one point, we had a piece of code from a Polish university that was written in entirely vowel-less mathematical Polish, which, of course, nobody had any idea even what it did. We had one function, one method, that was 32,000 lines long, whose name was process. And of course, nobody developed that. The lead engineer on this was a professional geologist. By the time I got to it, it had got about 5 years of development left in it. It had started with about 5, 6 programmers, but then it had grown to a team of 25 spread across 3 time zones. Like, that helped. We had a bug list. We actually had a whole support desk handling bugs, and the recorded bug list was 4,500 bugs. Now, we literally didn't know which of those were significant. We were trying to knock these bugs down, and we just were making no progress. So we thought, well, let's prioritize. So we literally deleted the bug list and waited to see which ones came back. After 6 weeks, 4,500 of them were back. Our velocity had slowed to an absolute crawl. We're getting an efficiency of about 2%. That is, for every line of feature code that we checked in, we were checking in diffs in another 49 lines, bug splatting the rest of the code. That's where our velocity had gone. Because of the worst management it's ever been my misfortune to experience, we couldn't do a rewrite. And actually, I think in retrospect, that was probably the right choice. So we thought, well, what happens? Let's just see if we can size this problem. So we said, if we took this entire team and put them onto nothing but bug fixing and remediation and cleanup, how long would it take us to clean up the bugs? And what we found was that we couldn't clean them all up, but we could put a serious dent in them after 300 years. So this is a project which was as much bankrupt as it's possible to be. Now, I should have had more sense. I should have quit at this point, but I didn't. I was saying, well, all right, we can't put them in. How are we putting them in? This is what Sander said in his introduction this morning, in his keynote, where he was saying that programming is the process of putting in bugs. And there's an element to that. But there's a codicil to this. You see, we had this feeling in the team, stop me if this doesn't feel right to you, but we had this feel that there was just bugs in the room somewhere floating around, and when we were at the keyboard, they'd dive in when we weren't looking. But that wasn't true either, because that's only ever happened once. It was here, back in whenever that was, 1947. That's the only time a bug has ever been caused by a bug. That was a moth that flew into the back of a computer and got fritzed on the high voltage lines and caused a short circuit, and that's what caused that. Now, the reason why our program had so many bugs in is because, who'd have thought it, we were putting them there. So I asked a question. I said, how were we putting them there? And this is the most important question I've ever asked in my life, because the answer really surprised me. It turned out we were putting them there despite our best efforts not to. I want to play a game. This is a real simple game. You all know the game. If you don't know it, you'll catch on real quick. Incidentally, the patterns that we saw back in that exercise, we have now seen in every single repository we have ever looked at. It's absolutely reliable. It is in your repository too. What we did was we asked 1,000 code bases, what was the activity? What was the cause of the bugs that were in there? There you go. What is the most common cause, or have a guess at any of the common causes? I didn't hear any of those. Shout! Yeah, I was looking at the mechanics of the code. I can't do anything about the imminent deadlines. All you can do is shoot the boss. Now, this is going to surprise you. We found null pointers. People missing null pointers and the null pointers tripping. Even in modern languages, that kept on happening. I think there's no excuse for that. But interestingly, this is not the number one case, and it was responsible for only 2% of the bugs that we found. I expected that to be a lot more. The next one was even more surprising. You know when you call a function and then you check the result of the function, or you're trying to catch an exception? That process itself was responsible for 4% of our bugs. Error checking creates bugs. And if that's not bad enough, the exceptions are even worse. Now, these they're sort of a type. They are the kind of things that match together. They sort of feel like not handling corner cases properly. But the next thing was even worse. This was something that at the time we didn't even have a name for, but I'm now talking about a string typing. This is when you say, I've got a date and it's declared as a string. Or you've got a name and it's declared as a string, or something like that. Or you've got a quantity, you've got a distance and you declare it as a float. Right? String typing is where you use the native types to be able to talk about something higher level, but you don't use a higher level abstraction to talk about it. And we find this everywhere, and it's responsible for a vast amount of bugs because they have the same kind of distribution, the way they trip is the same way that these trips. They're a different flavor of bug, but they have the same underlying mechanism. The same underlying mechanism, remember that. But this is still only 25% of our bugs. We still have one to account for. Any guesses? Sorry? Actually, no. No. In fact, we were so bad at it that added hardly any bugs. No, the number one cause of bugs in our program was debugging. And the funny thing is that debugging put in bugs of the exact same form. All of these things looked the same in code. All of these things are mechanically checkable for. And that was amazing. So this is my thesis. If we can do less of this, naturally we'll do less of this. If we can figure out how to stop doing these, if we can not put defects into our code, we don't have to spend time taking them out. And we don't have to take the cost, the reliability cost of taking them out. Do you think that's hard? I knew you were going to ask me that. I want to introduce you to this guy. Sorry, I'm getting ahead. This is Taiichi Ohno. He is the guy who invented the Toyota production system in Japan in the 1940s and the 1950s. At the time, the way they built cars was they would assemble the car, take it off the production line, and then they would quality control it. He said, that's the wrong way to do it. He said, if you are quality controlling the car, it is already defective. We need to be able to get the car off the production line, onto the transporter, and into the showroom without ever being touched. We need to have that much faith in our production line. He is saying something which at the time was impossible. It was anathema. The world had the same reaction to him as you just had to me, saying don't put the bugs in. Now, he built not just a whole industry, he built a whole way of thinking out of that principle. But he had basically two pillars to this. The first one was a thing called Kaizen. And Kaizen was this idea that a lot of small changes will add up to a lot in the end. If you can make lots of small improvements, then you get something much better than what you started with. Now, this is something which we all understand. We've taken this to heart. This is what lies at the heart of Agile. This is what lies at the heart of what passes for AI programming. But we understand what this means. But there was another principle which went hand in hand with that, without which the first one wasn't going to work. And this was the principle of poka-yoke. Now, what poka-yoke means, I mean, a lot of this is Japanese, so it's hard to translate, but basically the idea is, if you hang a door on a car and you hang it wrong, whose fault is that? Is that the assembly worker? No. It's the fault of the design that there's a right way and a wrong way to do it. If there's a right way and a wrong way to do it, then you can't blame somebody for doing it the wrong way because you've provided them with the affordance, with the facility to do that. Okay? We need to get that principle in place. Now, the next guy is Edwards Deming. He joined Ohno and Shigo, his partner. He's an American. And he watched what was happening. And in the 1970s, he went back to Detroit and said, you should see the way these guys are building cars. Do it this way. And the entire reaction was talk to the hand because the face ain't listening. Until the 1990s, when American cars had become so shit that nobody wanted them at all and the Japanese were taking over. Then people were taking notice of him. And he was famous for saying defects are not free. It costs you money to build something with a defect in it. It costs you money to find the defect, and it costs you money to take the defect out. You're better off not doing it in the first place. And he built this whole principle of Lean and Six Sigma, which was about that. And then, coming more up to date, this is Tom and Mary Poppendijk. They were very active in the 90s, in the noughties. They're very old now, and they're sort of disappearing off the stage. But out of all of these, they're still alive. But they have taken the same ideas. They've written books about lean software. And one of the things that they say is build quality in. Do not track defects. If you have so many defects that it's even worth tracking them on a piece of paper, you have already failed. You have to build quality in, and you have to obviate testing. Now I know what that sounds like. I'm saying to you, don't test your code. And you're going, what have we just spent the last 20 years persuading you to do? But I want you to have enough faith in your development practice that the testing is a formality. I want you to notice they're all smiling. Unlike, apart from when I crack the jokes, most of the people in this room. Okay. Now, they're dealing with machinery. They're dealing with industrial control, building cars, building airplanes. This is the easy stuff. We're programmers, right? We're tough guys. We've got a much harder job to do. Why is programming so difficult? Well, I think it's something to do with the nature of the things that we program. Because we program digital computers. Programming analog computers is not as hard as this. Programming even quantum computers is not as hard as what we do. And the reason why it's hard is this. It's in the nature of what a computer is. On the chip surface itself, the machine is executing instruction after instruction after instruction in order until it comes to a decision point. And at that point, it either continues on its way or it branches off somewhere completely different. And when it does that, it might be minor and come right back on again, or it might go off and turn into something completely different. Your phone might turn into a gaming system, or it might turn into a voice recorder, or something like that, because it will fundamentally change itself. The computer is doing this maybe 1 million times a second. Now, a machine with 1 million moving parts is a very complicated machine. But a piece of software with 1 million decisions, this is baby stuff, right? But the thing is that these decisions are not like the moving parts in a machine. The piston is always connected to the crank through the conrod, and they stay connected no matter how they move. These decision points are more like breakages, they're more like failures than they are like connectivity, than they are like joints, articulating joints. Now, can you imagine what it would be like to drive a car with 1 million failures a second? If you've ever owned a classic British sports car, you don't need to imagine it. You've experienced it. But other than that, but the net result of this is that when a program reaches a decision point which you're not expecting, which you haven't properly anticipated, you being the programmer, the user, one of your dependency writers, any of these things, then what it does is it goes into a state which is unknown and unpredictable, and it kind of amplifies the fault. It kind of amplifies the unexpectedness. So you have this sense that software feels brittle. You've got to baby it. You've got to get everything just right. But if something goes wrong, and things start to break off, and you get this brittleness that once it's gone away, you can't bring it back, which is why we switch it off and switch it on again. That's what makes software different to any other engineering. And I'm going to show this to you because the rest of the engineering world for the last 5,000 years have known different. Let me show you this. Does anybody know what this is? That's a building called Taipei 101. This is Taipei City on the north coast of Taiwan. Now, Taiwan is on the Ring of Fire. It's a fault line. There's volcanoes all the way around. There's not just earthquakes. They never stop. The ground is just constantly moving. So you can see that you can't build buildings very high because the ground's moving too much. And then right in the middle of this, they built this thing. How on earth does that stand up when these only barely can? Well, the answer is it's built to be stable. It's got self-stability built into it. So, right up on the top floors, there is this enormous ball. It's suspended on cables from the top, and it's resting on these gas rams, shock absorbers. And when the building gets pushed from one side, or when the building's starting to topple over, the ball itself pushes the building back upright again. That's how it stays stable. There's no electronics in here. There's no software. This is purely passive. It does it by itself. We see self-stability all over the place. In an aircraft, when you're driving in the car, if you hit a bump in the road, you'll feel it in the wheel, but The car will come back to its course naturally without you having to do anything. In an aircraft, when an aircraft's flying and it hits a pocket of air, it will come back to straight and level flight, even if the pilot's in the toilet when it happens. So, how effective is this? Taiwan was hit, Taiwan Island was hit by a magnitude 7.8 earthquake. By the time it hit Taipei City, it had got down to 6.8, but it's still a fairly serious thing. And so this, I'm sorry, I should have sound, but this is what it looked like at the time. And what you'll hear if you heard the sound was that there was an announcement to say there's a big earthquake, and people were just continuing to mill around and, oh yeah, and carrying on photographing because the building carried on feeling stable. This is self-stability. This is, if the thing gets knocked off course, it will come back on course automatically. This is the opposite of how software is designed. Software is designed deliberately to amplify disturbances. That's what throwing an exception does. That's what aborting a process when an error return value shows an error. It's the opposite of this. So that's self-stability. But there's another kind of stability which is even more important. You have all seen railway carriages sitting on sidings. I'm sure you have. Has it ever occurred to you to wonder why they don't roll away? How come they're safe just sitting there? Well, the answer is because of the way train brakes work. Let me show you what's going on inside of this. When you have a train carriage like this, each wheel, each axle has brake calipers and pistons which push the brake shoes onto the wheels or onto the axle. Okay, that's how it stops the train. Makes sense so far. The point is, you've got one of these on every pair of trolleys. So on this carriage, there would be 4 of these assemblies. And these things are connected by a pipe that runs the entire length of the carriage. The emergency stop button is connected to that pipe, and it's open at both ends. Now, on this end, you stop it off. But the other end is connected to the locomotive, which has a similar pipe running the length. And that's connected to a pump, which is connected to the engine. So when you start the engine, the pump runs. No engine, no pump. When the engine's running, the pump's running. But at this point, this valve, this is in the driver's cab, this is open. So this is pumping air into this system, and it's all coming out through there. When the driver wants to move the train, he closes that valve. This pipe pressurizes along the whole engine, along the whole train, and that releases the brakes. And now the train can move away. And when he wants to stop the train, he lets air out. And the system depressurizes and the brakes come on. And if a passenger in one of those cars behind presses the emergency stop, the entire thing depressurizes and the whole train stops. If it separates here, this section depressurizes and the brakes come on, and that section depressurizes and the brakes come on. And if one of these calipers fails, there's still another 3 calipers on this car and another 4 calipers on every other car that will bring the train to a stop. Basically, there is nothing that can go wrong with this system that doesn't revert it to a safe state. This is called fail-safe. Fail-safety is not a gadget which kicks in when the rest of the systems fail. It's the base state which you have to do work to lift out of to do some work. But the moment you let go, it falls back into a safe, stable state. This is how we build train brakes. This is not how we build car brakes. Just saying. And this is not how you build software. There's one more kind of stability that I want to show you in detail, and this is feedback-based stability. This is where you take far more power and far more control than you need, and then you use that to steer what you're doing, to control it. This is how rockets work, for example. So here's a rocket sitting on top of its fire. Has it ever occurred to you that this is like balancing a broom handle on your hand? Because you've got all of this mass up here and all of the force down there. If this starts to tip over, it's just going to spiral out of control. So what do they do about this? Well, as this starts to tip, then there's gyros in the top which know that it's happening. So it redirects the thrust and scoops it up exactly the same way that you would do if you were balancing a broom on your hand. Chap who invented this was Werner von Braun, the German rocket engineer, and he went to America to drive the NASA program to design the Saturn rockets. When you saw Musk's rocket coming back onto the pad, this is how it was doing it. And it's all done because up in the nose, there is gyros and accelerometers measuring exactly how this is moving. And then that is basically, it's amplified, and that's used to control thrust vectors. Sometimes they've got fins in the exhaust, and sometimes they move the engines. But how does that know how to control? Because that, the navigation system, tells it where it wants it to be. And this system does whatever is necessary down here to put that there. So you've got a huge amount of autonomy there. The stability comes from knowing what you want. But by the time you get over here, it does whatever it needs to do. This is very high gain stuff. You can imagine if that system fails, the rocket will just flip and spin and there's a Catherine wheel. And yet this is incredibly stable because you've got that feedback loop. This is how transistor amplifiers are stabilized. Valve amplifiers, tube amplifiers, don't have this. They're self-stable, and that's why they sound different. So that's three kinds of stability that engineers know. We have known, as I say, for 5,000 years, that if you want to build a reliable system, whether it's a building or a bridge or a car or anything, you have to build it to be variation diminishing. You have to build it such as to be stable. And we don't build software that way. And I'm going to prove it to you in just a moment. But just to summarize, these are the principles that I want to talk about, that I want to try and get in your mind. This idea of self-stability. Edgar Dijkstra talked about this in 1969. In 1988, Bertrand Meyer invented the Eiffel language, which was totally based on the idea of self-stability. And that's a language which deserves to be better known than it is. We've got this idea of fail-safety. If things can go wrong, we need them to fail safe. Guys, you've got to know that. Right. We've got this idea of feedback stability. We have these very powerful tools, so we need to bring them back under control. We need to tame them. That's what feedback stability does. And the fourth idea, the concept called anti-fragility, that was created by Nicholas Taleb. And the idea there is that a system which is impacted, a fragile system, you impact it, it breaks, the way software breaks. An anti-fragile system gets stronger as a result. So these trees that have fallen down and then they sort of bend and start growing up again, that's an example of anti-fragility. There's somebody tomorrow who's doing a talk about precisely this, so I'm not going to cover it a lot here. But these are all types of stability that come from engineering and from the natural world, which create long-term, durable systems that we can entrust our lives to. So what does this look like in software? Well, I want to show you a piece of code which I am hoping will appear, that's better, which I am hoping you will agree is a reasonable example of modern best practice code. First of all, what does this code do? Come on, I thought we agreed with all programmers. Anybody? Yeah, go ahead. Yes, and can you expand any more on that?
I just read the name.
Yes, exactly. All we've got is the name. Does the signature give you any hints? Not very much. Okay. Let me make the case. You said it's reading a CSV file. You're absolutely right. And in every single one of your heads, you have a picture of what that means. And I bet you're pretty much in strong agreement about what that means. You know what a CSV file is. You know all of the gotchas in parsing it. You know what that should be doing. How much of this code is actually doing that? Precious little. And the reason why is, look, we're babying the machine. We're finding all of the things that can go wrong. Do you remember I told you that error checking is one of the major causes of bugs? Well, here, we've got lots and lots of error checking. Here, we've got something, I don't know. And that's not all of it. That is the whole function. how much of that is actually usable? How would you test that? The thing is, if there is a defect hidden in there, it's pretty well camouflaged. And you can't test it. This kind of thing is inherently untestable because most of this code is talking about things that should never happen. They're talking about all of those corner cases and all of those error cases and stuff like that. Would anybody disagree with me that this is the kind of code that you find in the wild? Okay. Now, I wrote that code not to do something stupid, not to write really bad code. I'm capable of that as well, and I have another talk about that. I actually claim that this is an example of modern good code. But if I tell you that this started life like this, now do you know what it does? This is simple. This is absolutely telling us where we want to go. You remember that navigation, the rocket navigation? This is our navigation. This is telling us what we want to achieve. Now, I'm writing this in sort of an archetypal code. So I'm taking a few shorthands. Things like split via CSV. That's somewhere else. Whatever CSV means, it might mean something different as we add things to the format. It might mean something different as we switch to Unicode or to something else. But the thing is, it's named. We know what it is. We're not trying to cram it all together. We've got this idea, zip. What does zip do? Well, it creates a dictionary out of two things. So now we can see what this is doing. This is creating, we've got a header line, which it reads here, with all of our headers in, and then it creates a dictionary for each item on the line, pairs it with the dictionary, pairs it with the header items, and then yields that as a dictionary, and we do that over and over again. Really simple code. You can understand this in 10 seconds at first glance. My claim is, reliable code looks like this. Wouldn't it be great if all our code looked like that? But, you're saying, what if there's a blank line? What if there are no lines? What if the file's not even there? What if you read it and it's not an integer? What then? And I say, that's what your fail-safes are for. That's what your stability is for. You let your stable systems, you let your stable results deal with that for you. So, for example, what happens if it's not an integer? Well, you hand back a not an integer. You see, you've already seen this. You hand back something, a null object. You hand back something that exports the integer's interface, but isn't an integer. Doesn't do anything. I'm going to show you in a moment what that means. What happens if the file doesn't open? Well, what's the difference between a non-existent file and an empty file? So just carry on, just don't iterate. What happens if we open the file and it's empty? Well, we don't get to read the header. So that doesn't read anything, but then the repeat fails. And we don't get anything. And this stops silently. This just, if you hand it something which it can't parse with, there's nothing in there to work with, it hands you back an empty iterable, which the client of this can rely on. No error checking necessary, because an iterator that doesn't iterate is still a valid iterator, right? Now, if this wanted to signal that something was going wrong, it could. It could send out special objects. At the very least, it should be speaking to a log file to say, I've logged the fact that this has gone wrong. But what we are doing here is we're protecting the happy path. Does that make sense? I claim good code looks like this. Reliable code looks like that. And what you just saw, the previous example, that can never be reliable. The kind of defect which causes the bugs to balloon, that previous example was full of it, and this isn't. But what you do have to do is to have faith in your fail-safes and your stabilizers. So what do those look like? I'm going to pick out just one. This chap is Tony Hoare. You know who he is? Here's the guy who invented null. He did it when he was designing Algol back in 1968. And he put it in because he said it would be no hardship to implement. And then he watched his horrible creation unroll across the world until eventually, this was a few years ago now, he admitted it was his billion-dollar mistake. You've all heard this quote. We have known for a long time that nulls are toxic, and yet somehow we can't live without them. Even when C# tried to build in null safety into the language, when C# tried to build in null safety, they got it wrong, and it wasn't safe. And you had all sorts of special cases around the null safety, which spoiled the whole idea. But there is something about nulls which means we can't give them up. They're toxic and they're horrible and they're like vaping, but we can't give them up, right? So why? What's going on? If we see, this is probably the simplest code example you will see in this whole conference. If you see something like this, then what you're saying, what does it mean? I think is that you're defining some variable which implements T's interface. Now, it might be an example of T, it might be a concretization of T, it might be a subclass of T, it might be an implementer of T. But the point is that whatever else it does, whatever else it is, it implements that interface. Would that make sense? And if we make an assignment like this, then what we're saying is that either Q also implements T's interface, or that there is some suitable constructor to convert the Q into something that implements the interface. But that's not what it does mean. What that really means in today's world, in modern languages, is what it should mean is something like that. It should mean a basic version of T. It should mean something about which we know very little. What it actually means is that, which is not a T, and has a completely different interface, and does something completely different. And that is the reason why nulls are so much of a nuisance, because it means that every time you use, in something like C, a pointer, or in something like C# or Java, anything, you have to check whether it's nullery or not. You've got to figure out what its type is before you can use it safely. And nobody can remember to do that. And even in languages like Rust, where you've got, is it called the variant types or the union types? I've forgotten what the language is in Rust. But where it can be either some, something, or none. You still have to test. It's just forcing you to test. Because what are you supposed to do with this thing when you're expecting a date and what you've got is I'm not a date at all, just a digital problem. I think what that should mean is this. It should mean something that exposes T's interface in full, but provides no information when it does it, not even identity. Now, the reason for that comes from group theory, which I'm not going to go into now, but the idea is that there is this sort of least defined thing. And you can propagate that through the system, you can compute with it, it's safe for anybody else to rely on, even though it's not doing anything useful. This is a failsafe. By definition, this is your base state on which you build all of the behavior that you want. But it means that you can start off, you can mash up a system built entirely out of nulls, and prototype it and test it, run it through your debuggers, actually see it working with no data flowing through the system at all. So this, as an example, in code of a failsafe, exactly the kind of thing that I was asking you about. This is what you see in the train. Does that look unfamiliar? It shouldn't, because we already have them and you use them all the time. This thing is a double about which we know nothing. We've tried a computation, it hasn't worked, it's given us back the nan. But you can compute with it. You don't need to stop there. The nan propagates, and it affects everything else it touches. You can never get back to a real number, but you don't need to bother about it until you get to the end of your computation, and you need the actual numbers. So we already have this process built into the very concept of floating point numbers itself, and it works for us. The guy who designed this was the guy who designed the floating point format. It's called Kahn, and he is an absolute genius. The things that he built into that standard. Okay. So, let's talk about the difference between a null pointer, and I know that Java and C# don't have pointers, but the difference between a null pointer and a null object. You're all grown-ups, you don't need me to read this out. But this is the contrast between the two. These things are unsafe. These things are unsafe, like the car brakes. These things are safe, like the train brakes. These things amplify errors, because each time you've got to test it, and when you test it, you've then got to find another meaningful route to take. These things are variation diminishing, because even if you've got this as a result of a malfunction somewhere else, you can carry on with it. You can stay on path. You can stay on track. You might get knocked off course, but it will return you to straight and level automatically without you having to reach in and do anything. Now, this is just the tip of the iceberg. There's a lot more that I could talk about this. I mean, I've got various talks. I've got long courses about this. But I just want to summarize this idea that the reason why software is brittle, the reason why it's difficult, the reason why we get phoned at 3 a.m. is because we write our software such as to amplify disturbances. You get a slight disturbance and it goes out of control, like the uncontrolled rocket, like the glass breaking. We deliberately write our software to work that way. We've got processes like error return checking to make sure we amplify these disturbances. That's why error checking is such a huge cause of bugs. And as for exceptions, what exceptions do is they say, well, just basically, you leave, you say, this is not my problem anymore, and you jump out of the building, and you don't even know if there's a safety net waiting for you. So what we need to create stable software, what we need to create reliable software, is to create stable software. And you've seen the whole point of these types of stability is it does not need to be perfect to work perfectly. People always say to me, you can't ever make it perfect. And you're right. But I don't need to, because I have made it so that every imperfection gets smoothed out automatically. Does that make sense? Okay. Now, I said at the beginning, I started my career, I didn't say this at the beginning, this is just an aside. I started my career building aviation systems, and this is how we built them. I built medical systems, and this is how we built them. And you're thinking, okay, so we can't have space standard and aviation standard and medical standard code in our systems. But let me tell you this. It takes much less time to do it right the first time than knowingly to do it wrong. I have a model, if you've ever seen my technical debt talk, I have a model that shows that even the most unbelievably good teams will get 3 times improvement in velocity by writing like this than by writing naively. Adam Thornhill, who operates CodeScene and wrote Your Code as a Crime Scene, has experimental evidence that shows that you can multiply the effectiveness of a team by 10 by doing this. This is not even a theoretical model. This is real experience. So this is not the expensive way to write software. This is the cheap way to write software. Because you don't have to do any maintenance, or at least very, very little. Now, I said at the beginning, I feel strongly about this because if we can't get software to work, we can't get anything else to work either. So, I have written a book about it. This is my book. That's where you can get it from. There's a free sample. There's 400 pages of it, and I don't expect you to struggle through it because I know nobody reads books. But what we talked about here is just the first few pages of this. There's a load of stuff in there which talks about specific patterns and the things that you can do to leverage that kind of pattern. It's got layers and layers of how you protect your software and stabilize it. But that's what this book is about. So there's the barcode. Go and get it. Enjoy. Thank you. Just to check, everybody's still in the right room, yeah? Okay, any questions I can answer? Sir, you're going to have to shout. No, not at all. Sorry, the question was, it's very succinct, so what happens when you debug it? And I think that the implication behind your question is there's things going on behind the scenes where you can't see it. Okay, well, first of all, your debuggers should be able to trace into that. Your debugger should know what those iterators are. They should be able to see things. So you should be able to say, well, this is not the result I'm expecting. And particularly, if you're starting to get error values back, then not only will the debugger show you that you got error values back, you should have some kind of instrumentation somewhere else to tell you that the error value has been generated and why. If there's nothing else, it should be in the log, or it should be coming out of your standard error. But my experience is that it's very much easier to debug this because your context is very much smaller. If you're getting a result back as a result of the file being malformed, you've got the file, and you can see the malformation, and you've got the thing which is objecting to that malformation, but you're still carrying on. You haven't got, you're not sort of somewhere over there because you're trying to track down an exception that's thrown you who knows where. So in general, because it stays where you are, and because it's self-stabilizing, and it's constantly working with these small contexts, and you find with this kind of code is that the functions are very, very small. When I was being taught to program, I was taught no function longer than 12 lines. Well, I think that that's humongous by these standards. I don't stick to that anymore. And I know that a lot of people will say, well, that's just academia. But no, actually, these functions come out really, really small, so they're very, very comprehensible, and you don't need to think about them. So for all of those reasons, I think that debugging is much more pleasurable when you're doing this. Yep. That's the stabilizing rather than the fail-safe. The fail-safe was things like the nulls. Yep. Okay, that's in the book. I've got several chapters about that in the book, so I can only summarize this very briefly. But the answer is this. When you throw an exception, what you're saying is, I want to go somewhere else, just throw it away. I can't handle this, it's somebody else's problem. But we have another way of doing it. The reason why that's so destructive is that if and when you catch the exception, you've lost the context. You've lost the thing which caused the error. You've lost the client that wanted the result. You can't rebuild from that. You've also got a lot of side effects lying around. So you have memory leaks and all sorts of rubbish. But there's an alternative way of doing that, and that's to call it as an interrupt. Now, this is something, the way the chip works itself, where it gets to a point where it can't continue, or something's happened, you've pressed a key, or particularly, we use this for page faults, when the memory isn't in physical memory. And so this triggers an exception, and everything gets suspended. The state gets pushed on the stack, wherever it is. It goes off and does some processing to try and remediate what was fault. It pages the stuff back into memory or whatever it is it wants to do. And then it resumes where it left off. And the client program, the thing that's been interrupted, has never known that anything has gone wrong. Now, I think that when you do this kind of error handling, my claim is, number one, you shouldn't need to, because you should have the stabilization systems keeping you on track. But where it's desirable to do so, you should do it in an interrupt-like fashion, so that you're not interrupting the flow of the program. You might interrupt it in time, but you're not interrupting the flow. You're dealing with it then and there. And the response from that will tell the stabilizers how to continue. So you might say, have another go at reading it, have another go at opening it, pretend it's empty, whatever. But the point is that you take that decision when you're handling the fault condition, or it's not even a fault, it's an exigency. But while you're handling the exigency at the point of use, because by the time you've come out of that, you are now committed to the result of that. It is either a persistent error or it's not. And that's exactly the same that's true with exception handling. Does that answer your question? Okay. Okay. I understand the question. I'm sorry, I'm rushing you because I'm almost out of time. The stuff the code samples that you've seen are written in a synthetic language and sort of an archetypal language called SNS, which I've been working on. I am compiling it, I'm parsing it. I have high hopes for this language, but on my own I couldn't possibly build an ecosystem around it. So if anybody has spare money, I'm looking for sponsorship to develop this language. Absent that, you can do this in any language. I have done this in C, I've done this even in assembler, but you can literally do this in any language. There are, again, in the book, I've got whole strategies about how you can construct those null objects mechanically, how you can construct those interrupt handlers mechanically. You can do this in anything. This is no more different in philosophy from, say, structured programming was 30, 40 years ago. It's a way of thinking about what code should be. I'm out of time. Thank you very much for coming. I'm here for the rest of the day. Buy me a drink.